something like the superfetter machine, and it will be very useful for us. I will show you at the end of the course of today, then how we can update, how we can save different when we use Bergström to learning and breathe things on some non-linear data sets, and we see some effect from superfetter machine actually. Okay, so okay, so let me check it. I recall this. Okay, thank you. There's somebody who already record for the video, so thank you. Okay, so let's go to yeah, problem like linear classifier where we have two class like +1 and -1 here. So there's some denote here, right? So we have like -1 here will be this class, and here will be like class of +1. Okay, great. So how we can classify this kind of data which using some wave vector and the filter vector that we already know, right? And where actually this X vector is where we extract the original data to the some kind of filter vector, and then we can project this kind of filter vector to this with its class like in the two-dimensional like this one, right? But actually, this filter vector it could be like high dimensional vector, like it could be like more than two-dimensional, like 3, 4, 5, or even 100 or 200 somehow. But where what we are seeing here is where we project this kind of data on the two-dimensional data, so we can have like some picture is very beautiful like this one, right? Actually, this data is quite not so half like non-linear data set. Like we can see, like for example, like it could be something, some class of the -1 will be somewhere here, right? And and this will be very more harder than it will be harder to classify some kind of this data set than this one. But okay, so we can use some like linear classifier. We are already learning about, for example, like we're building our Bergström with some formula like the sum of all the wave vector and the dot product with the filter vector, and then we make, and then we can make an something like decision on how it will be like positive or negative based on the this formula to calculate from the by this formula. And also we can use some beam method. It will go on like a bias here in this model, and finally we will make an positive or negative with this psi functions. Actually, yeah, here in that what we are trying to make, how we calculate the probability that will be for the at the end we will have for this using this this kind of formula. Okay, great. We can using this linear classifier like this one to classify make an hyperplane like this one for this kind of data set, right? Okay, great. We might have update somehow this our way vector like this, yeah, like somehow it will be make our decision will be well enough to classify for the data sets. So yeah, the question here is how we can make which one will be optimal between this hyperplane this decision boundary, and how we can dealing with this kind of problem. Okay, so we have something like, say, machine here, like so the machine is something like will be the boundaries between this line, and this boundary will be like it will be the y. So with this y, we can somehow mix with the glass will be closest to this y. For example, like we have like glass positive one here, right? And will be here, and a glass of negative -1 will be here for this two boy that will be present on the two-dimensional space. So what we are trying to do is we will try to make this machine on this width will be larger as much as possible. That means why? Because when we have a lot of like when we make a decision about battery on hyperplane, then we need to define which will be the largest machine between the closest boy data boy of these two classes. And with this kind of width machine, then we can tell that we have an hyperplane will be good enough to classify our actually classify for that to glass, right? So yeah, the aim is like we try to maximize this width from the hyperplane that we have learned, or we have created using this formula, right? So how to do that? How to know that we have an when we are already calculating for this linear functions or linear classifier, then how we can know that this width will be the maximum with this kind of hyperplane, right? So so can everybody like know like to say something like how we can know like will this width will be like the maximum, how do we know that, and how we can do that, like how we can define for this width for some language. The thinking, yeah, like because we for example like we can build on have a blend on the decisions but actually the hyperplane like this one, right? It look a little bit different with this one, right? With this black light, somehow we can update our way better with small value with much jump, for example, like this. And then we can at the end we can make decisions on the hyperplane like this one. And how do you think about this one actually compared to this black line? Okay, any idea here? Yeah, it's not easy at all, no, right? Because like um, but we can try something on this picture, for example, like to give a solution for this problem. We can see it's very directly from the picture, because you know, like when we are studying, we actually in the machine learning, for example, like this like, because we are working with a lot of number and also like, you know, like some y vector, some filter vector, a lot of things like it's only like numerical data, and we are something somehow we lost in our directions. And visualize in a way that will give us a way to thinking, like why this happened like this one, or like why this will be happen like that one, for example, like that. Visualize a very good strategy to build, and for example, like to how to see the data it look like, how to see the for example, like the hyperplane or hyperplane after we are running our algorithm, and it will give us an deeply understanding what we are trying to do. Yeah, and of course in this picture is also give us an a method to see how to maximize maximum this machines, right? Because what we are trying to do at the end, we need to build an hyperplane will be well enough to classify, to separate this two kind of the class, and then with this we can saying that, oh, my algorithm is learning very well. Uh, yeah, and this will be this one. This width will be like uh, will be a very important one. That's will give us a way to uh, to make up now, like oh, okay, the hyperplane that I'm training, I'm learning, a building here will be fit enough to that data, right? So come back to, yeah, come back to this problem where we have another, for example, like when we have another hyperplane, when we can this one might be something so ugly, so we might go to white. We might have an hyperplane like this one. That's okay, right? And we see that we see that okay, I can build an hyperplane here, right? uh, and I can make some machines to some data boy that will be closest to this hyperplane. For example, like I can draw on something like this one. I will have something like this. So yeah, I can have on width on machines for this. It look like because you know, like what we are trying to maximum this machine, that mean when this machine we meet cross this the data point which is closest to this machine, and then we're saying that okay, how far from this this closest data point to this machine, to the hyperplane that I'm building, and then I know that my hyperplane will be good enough to classify for that data, right? So in this case, we see that, for example, like here, in this case, a little bit ugly here, but you can see it's very narrow here, right? That means with this matching for this hyperplane is will be not good enough like the black one we have here, right? So that's why we have the matching here, which is the closest data boy will cross with these matchings from the hyperplane what we are building, and then we see that if we have maximum if we have this width of matching more larger, that means we can claim that, oh, okay, I have built an hyperplane good enough, will be like what width enough, large enough to classify for that problem, for that data. So okay, so that's mean for this to this maximum to maximum this matching, we see that it will compute from where actually for this matching it will compute from the closest data boy of this, for example, like in the class of positive class, we have this data boy will be here, right? So I from this data boy I can calculate on distance, right, from this data boy to this hyperplane actually, yeah. And also I can also can compute from this closest data boy to this hyperplane as well. So that means when I create training my model somehow, it will create my hyperplane will be good enough to make this matching will be largest enough. Then I will have some good hyperplane to make under decisions on to classify for that two class, right? Okay, are you agreeing with this one? Do you have any question so far to like this one? You don't have anything to say? No. If you don't understand, still please ask me. I will explain this again. Otherwise, you will like you will lost in this, and you might like don't know how to go so far for this lecture, right?
Could you explain again?
Okay. So okay. So actually, it's here like let's say here, right? What we are trying to do is to know which is the hyperplane will be the best or the optimal one, right? Because we have many line separator on the hyperplane we build, which when we train in our data, and then we can build some hyperplane like this one. For example, somehow we train our first model, we get this for example, like in position, for example, like we can have an at time t1 at 10 o'clock, for example, like I can build a model, or with this model I can make an hyperplane like quite good enough to classify for this two class. And for example, but I'm not satisfied with that problem, so I'm going to train my model again with another parameter in tau. For example, like I change from 0.001 to 0.5, for example, like that. And who knows, my hyperplane will be changing like this one, right? With the black and the rest like this. And if we see that if we have a machine will be maximum, that's on machine that is on width from the closest database on the class. For example, like in the class -1 a positive class here, we will have on database will be closest to this hyperplane, the black boy line here, right? Where we will have like we can calculate this this distance from this to this hyperplane. Yeah, that is the we say like a machine will be the closest database to the hyperplane. And also we will have a method to calculate for the distance from the negative class to the hyperplane like in the black one as well, right? So we will have actually in the end will be the sum of the two distance from the machine we see here. For example, like in the yellow rectangle here, we see that it will be the sum of this positive class to the hyperplane, and from the negative class to the hyperplane we have like for the black line here, right? So I might have another model. We training this model, and then we will have another hyperplane. And with this hyperplane, we can also calculate for the distance from here from the positive class to the this rest line on this hyperplane somehow. Yeah, with the same method, we are calculating for the yeah for the distance. For example, like from a boy of negative class to the this hyperplane will be like in this red line, and we will have another thing like here. We calculate in the distance from the positive class to this hyperplane, like the rest line here. Then we see that this will be optimal than the two class we somehow we see in the way we are calculating for the distance from a boy to a line, and then we see that, oh, okay, I had this margins of the rest line will be smaller than the margin of the black line from the two closest data point, like that's one, a negative and positive line, that's one, and then I can make a final decision like because the distance, the sum of the positive class to the hyperplane of the rest line will be greater than the no, it will be smaller than the distance we'll calculate from the positive class to the hyperplane of the black line and the negative class from to that black line as well. So I can finally I can make an assumption that the distance from we say the distance from the black line will be somehow greater than the distance from the red line to the positive class and negative class, the closest one. So I can say that, okay, because I had this hyperplane, actually this machine will be larger in the width of that margins of, so I can make a final decision. Okay, I think this hyperplane will be optimal than this one. Will be optimized on this one. So I choose this training model to classify for my data. Otherwise, I will choose this one, right? Are you agree? Are you agree? No. So how? No. Or something we still didn't understand or something. No. Okay. By the way, okay. So we are saying here. Okay. Thank you, Minh Trung. You understand now. Thank you. Okay. So yeah. That's why we trying to make an we make try to maximize this margin to ensure that we have a very good training model with the decision line in the hyperplane. After we use some formula to calculate the formula by the sum of all the wave vector and the theta vector what we have, and then finally we okay, as I can check that this margin of this hyperplane will be right enough. So I choose this curve parameter, this wave vector like this one, the bias like this one, or some small value like tau value somehow to updating our weight vector other one. Yeah. And yep, so we can know that okay, when I have on maximum machine like this one, then my hyperplane will be good enough to training for this data, and I will choose this kind of model, the parameters like this one to um, to learning for this kind of data, and we can test on this on another test set, for example, like this one. So okay, so now we see here something like we say like how we the distance from the closest data point from positive class and negative class as well. So somehow how we can calculate this distance, for example. Yeah, I know that you are very good in mathematics when you are in the high school, right, where we are learning a lot of things like derivative, something like how to calculate from or to a distance or some kind like that. And now is the time for us to apply that kind of knowledge to this problem, how we can calculate from the distance from an data point on the space to plane or line in this example. Okay, so how we can do this one? Either the way we can know how we can have a good machines to ensure that what we are doing with what we are created from our hyperplane will be the optimal one. So we want to say something. Okay, yeah. So okay, so this data point, this closest data point where we are saying it will be on super vector. Yeah, so that's why here we have a name of like something like super vector machine, right? So actually, yeah, what we are trying to do here, we will calculate the distance from this super vector, for some because we know that this super vector will be something like the filter is our filter vector, right? Where we can have when we can project this kind of filter vector to the space. First of all, here we will have like two dimensional space where we can see in on the axis like x and y here. So okay, so this data boy where we are calling is will be on support vector, and from this support vector we can somehow we still using our knowledge on calculating the distance from the a data boy vector to another to a line a hyperplane here, and then we know that okay this with this hyperplane I can have an machine from the two of this super vector by calculating the distance from this kind of super vector to the hyperplane, and then I will know how large of this the machine, and then I will decide at the end which one will be the good one to make a hyperplane. Okay, so how we can actually how we can calculate this yeah distance for yep. It will be like here where we will have something to work on mathematics actually. Yeah, so well I might have something for you here. Okay. Wait a little bit. Yeah, something in the mathematics, and I hope that will be funny for you as well, right? So as we know until now, right, where we will have an hyperplane where we train our model with kind of this formula, and at the end we can make an hyperplane like this one. For example, like we can have a hyperplane like this one. Sorry, wait a little bit. I think yeah. Wait a little bit. Yeah, I have something. Okay, so for example, like we can make an example where we with this formula, right? When we can make a decision, yeah, it's like a particular. For example, we can do something like this one to understand how we can have an hyperplane with this formula like this one. So for example, like if we can make a particular model where we can, for example, like we can make an linear classifier like this one, like to I assume that we can have like very simple solution for this class when we build on the hyperplane where we will like the way vector line look like in project two dimension, and then we can have like 2x minus the b here will be like -1, and what we are trying to do we build this with this hyperplane at the end with this method. So we can see here, for example, like when I have x equal to 0, and then I will have y equal to like -1, right? So I can have an over here. And when I have like x equal to 1, then I will have and y will be like 1. So I can have on yep on yeah, like this one. That's mean okay, I can build an hyperplane based on this kind of linear classifier like this one, for example, like this one, to make you understand what is us formula, for example. Yeah. But actually, in the high dimensional, like when we have lots of 100 filter vector and 100 wave vector, and then of course we couldn't have like something like linear function like this one, right? So we try to project something similar for you to understand, too easy to understand this one. So yep, assume that we with this hyperplane, then this line, then we can make an hyperplane like this one, more like this, and yeah, so we can have a very good hyperplane with black line like this one, right? So this one actually we also can assume to like, because we are learning in machine learning, so we might have okay, I will have like with this two-dimensional vector, so I can rewrite something like this one. So I can rewrite something like, I will have like, here will be like x1 and here will be like x2, for example, like this one. And then I will have to rewrite this formula for example, like it will be like x2. This one will be equal to x2 equal to here will be like something like, we can say like m and x1. Yeah, some x here now, right now we can write something like x1 to become x1, and this -1 here we can generalize this one. This problem like it will like plus b, for example, plus c or something. Yeah. Actually, we can say some. Okay, I will have this formula, and okay, so I can translate this formula to, I can write this one like this one, right? So I can write this one like m x1 minus x2, then plus b equal to 0. Okay, great. I can write something like this one, right? So I apply this this one. Okay, so I can rewrite this one. It will be equal to something like m and -1 and multiply with x1 and x2 plus b equal to 0. Okay, and you agree? Okay. So here we can say that okay, if here look like I will have something like here, right, and x here I will have something like for this filter vector, it will like, this will look like two filter vector like x1 and x2. Even if we have something like three-dimensional, then we will have like x3 and x until like xn, where xn will be high dimensionals filter vector for them like this one. So we can say okay, here will be an way our vector will be in the two dimensionals, right? So we can so that I will have ways here will be like this one. So I try to multiply with this one, so I have to transpose this way. So it will be equal to m1, right? Okay, so our formula right now is can rewrite by after this, so we can say writing our formula like W transpose this one dot product with x plus b here will be equal to 0, right? Are you agree? Okay. So yeah, you see, so here we had a wave vector with a transpose vector somehow when we created some wave vector and then we transpose it to multiply with some dimensional, for example, like 2-dimensional here will be like x1, x2. We might have a future vector will be more complex and more higher. So we can write in this into this formula. Okay, so right, so how I can actually so in this we see that somehow what we are trying to do is when we try to compute an database from X, for example, to the hyperplane, and then we have to apply something like we have to project this kind of database, for example, like when we have like this, we go to x0 to y0, right? In like this one. So we what we are trying to do is we try to project this to an when we want to try to compute for the distance from a ball to a line. That means we are going to compute the ball from X to this this line will be Wx plus p equal to 0, right? From this X. Then we have to find a way to project this X to another vector. For example, like here will be we are saying that this will be on wave vector here. But we know that to calculate for this distance when we project it like this, then we have to prove that this vector, this wave vector have to be like an orthogonal. We are saying like perpendicular to the hyperplane that we are trying to build. So how we can prove that this wave vector W is always orthogonal or perpendicular to this hyperplane on this decision boundaries. Yeah. So we might use this formula because what we have until now like something like we trying to transpose our wave vector like this one, right? And we must to prove that this wave vector will be like always will be perpendicular or orthogonal to the hyperplanes. So we have this formula first. We are saying 1. So we can see another example here. In this hyperplane where we have like two that other database will be in this in this line with x1 equal to like x1 y1 something like this one. Yeah, and it's actually in this one. Yeah. So like, yeah, with this in this line, and then what we are trying to do is we will somehow to calculate the difference between this, because we have the difference between these two database will be like it's good like will be the x1 we minus to x2 somehow in this line, right? So we will have the formula to see here the difference here we want to calculate will be, yeah, what I'm trying to do here is I'm trying to prove that this way better on way like will be on will be an orthogonal to the hyperplane in the Division boundary. Yeah, so that's what I'm trying to do right now. So we yeah, actually here we will have an different here will be x2 and x1 here. When we have to the better, so we can calculate the difference between the beta x1 from the origin to this one, and the difference with the beta x2 is will be like from here to here, right? So we can say last we will have an x1 plus this difference will be equal to x2. Okay, and you see with this better transformation, then we can do something like this one. Okay, so from this I can yeah, implement that. I will have an again inline that I will have an difference will be equal to x1 minus 2 x2 minus 2 x1. So, okay, yeah, something like to proving this, and we had to figure out something different, and it's like funny, right? Okay, great, but we will have something like this one. Okay, so what I'm trying to do is still to prove this one problem, right? So okay, so how can I do next? So if we understand, we will have from the formula 1 here, then we will have we will have a formula for the two x belong to this line will be written like this one, right? We can translate this to this. So we will have an okay. We can rewrite this one by using this formula, and this one we can also have an x because x1 and x2 belong to this line, so we can have x2 as well. Yeah, consider all right. Then we can subtract this to formula to together, and then we can have like x1 minus wt here, and the transpose of the wave vectors thus with for example like x1 minus x2, for example like this one. Okay, we can have, and it will be equal to 0, right? Because we are subtract this one, so we we can have formula like this one, right? Okay, great. So we have here another formula. We say 2. Okay, so, and what we remember here until now, like if we have a dot product between the two vector and is equal to 0 from this non-zero vector, and then we will have, and then this y vector will be have to be perpendicular to the line. This line here will be like x1 minus x2 like this one, right? So yeah, that is the way we prove that this way better is on. We see here it always will be orthogonal to this hyperplane with this kind of proof. Okay. Are you agree? Somehow, yeah, I'm still I'm still looking back to my mathematics to working on better problem. Okay. Oh, great. I will. Yeah. Very good. I will. So you, if you understand this one, so you have a very good method. You are very good mathematics with you. Like yeah, you have a very good tool for this. Okay. Yep. So I'm trying to prove here is my way vector when I'm created here is will be always like orthogonal to this kind of like this hyperplanes actually. So okay, come back to the main point. The main point, how we can calculate the distance from a point to a line. With this proof, we see that the way vector here is the vector we can project our x. The data point here will be x to this way vector, and then we can calculate our the distance. Actually, here will be like when we want to calculate this distance from x to this hyperplane, it will be equal to the problem of when we project this point to this way vector, right? And then so we can have the similar distance here from this way vector to this hyperplane. Okay, so you got the idea right now, right? So yeah, if you still have something like to review, to make a review how to calculate for Apple to align distance, somehow you can go into some website like this one to see how we can do this. Actually, yeah, but we what the important thing here is how we can saying that okay, I will always have way on better that I can process my data point to that, and then I can calculate the distance from that with better actually. Yeah, and I prove that okay by prove that the way vector is always orthogonal to this hyperplane on this line decision boundaries. That means I can project my data on the space and to this vector, and then I can calculate this one by using some formula like boy to lie with distance with two dimensional problem like in this website. So you can go directly to this one to see how to calculate about this. Right. Okay. Yeah, we are saying that's the same thing. We here we can see in this problem where we have this boy x. Actually, I can call it like p1 with the coordinate like 0, 0 and y0, and when I project this to this y vector, and then I will have another point like p2 will be x2 and y2, and the voice will be project to the hyperplane will be like q here will be like x1 and y1, and by using the formula provided in how to calculate from the point to this distance using the y vector, and then we can have this actually this distance we are going d equal to here, like yeah, when I'm project it to here, so it should be like this also will be d here. So this distance so the distance of x actually what we are trying to do to calculate, right? So it somehow will be equal to yeah, to be calculated by this formula and divide by the magnitude of the vectors, the and make a square root here. So yeah, yeah, and yeah, the distance, for example, like in this case, this x will be here, right? Even in our machine, what we are trying to do is to calculate from the closest data point with the half length, right? For example, like we can have like here another x around x prime, for example, and we can apply the same thing to calculate from the distance from x prime to the hyperplane like that. Right? So yeah, well, we can use this to calculate for the distance from the data point to the align with like this one. Yeah. This is okay. So we have here until now, like we will calculate, for example, like with this x prime of will belong to the positive class, and I might have this one will be like no, I might have this one x plus 5. I say here will be x plus, and here we will have like x minus will be this part, and I will have x plus will be this part. We are trying to calculate the distance from the point which is closest to the margin, and with this one with the hyperplane actually then I can calculate by the two distance like this one, right, with the formula here. So I will have for example like the distance from x plus will be plus with the distance from x minus. It's my margins, the maximum margin that I will have to now. Okay, and I have formula to calculate for this one, right? So it's will equal to this one. So I can rewrite this one like this. So this one will be like x plus p divided this. Plus with this. Okay. Right. Right. Okay. So what I want to do here is I want to maximize this one, right? I want to maximize this margins, to maximize this. Maximum this margins actually. Yeah. At the end, I somehow, because I know that's with calculate with this distance, when I have this maximum of the two data point from positive class and negative class to the hyperplane, then okay, I will have a very good it will be more larger, then it will be good enough for the better the hyperplane I will try to learning with our model. So so here what we are trying to do is to maximize this one. So we try to maximize this one as well, right? Yeah. Okay. that is the same problem that I can do until now. Like, but I want to maximize this formula actually. So because we are now in this one, because we have this filter vector will be fixed, this bias will be fixed, and this one so, and the wave vector we are created here will be fixed. So we might this formula on the numerator in here. So we only care about this one, like the way, right? So if we want to maximize this formula, actually it would be like the same problem where we want to minimum this one, right? Minimum this actually something like one. Yeah. So what we are maximizing for this machine is we change into problem of trying to minimize the wave vector somehow with this magnitude of this vector where we will have our vector will be run from 1 to D because we have on what we want to showing for this one. So at the end we will be changing our bottom to minimize this formula actually. Okay. Somehow okay, how we can do this actually is it look like the same problem that we are seeing in Bertrand, right? Where we also doing the same thing, try to minimize the wave vector with something like this one, right? So can we apply the same method to this support vector machine using no using what we are doing in the Bertrand or not? Actually no, right? So yeah, that's why we go into another thing will be more interesting to minimum for this kind of way better actually because actually in the way we are trying to minimum the better in Bertrand we try to plus and we and minus with the tau value multiply with tau value with a very small number. We multiply with the filter vector we have, right? But in this case, we so actually they still in support vector machine they use another problem or another function that's to update for this kind of to make this wave vector will be optimized minimum for this one using the Lagrange multiplier. Yeah. Okay. I don't know if you are familiar with this Lagrange multiplier optimization or some kind. Actually, the idea of this problem is will be like where we have an Lagrange functions, and what we are trying to do is we're trying to optimize this functions fx, and based on the another constraint, we say the constraint will be like another function like gx, and this constraint will be multiply with an number, will be a number that we also can learn from the our training data. We can set it like some small, very small value that we are already sees in the Bertrand problem as well. So yeah, and we see that what we are trying to actually the Lagrange multiplier optimization is to find minimum of functions. Yeah. So what we have here it will be the same thing as what we are trying to do, right? When we try to minimize for this function this way better as well constraints. So we can apply this actually in support vector machine. They apply this method this knowledge to to for this Lagrange multiplier to minimize for the function that we will see here, right? Maybe we will have like because we are trying to do we try to minimize these functions, and with some constraints. How can we define for the constraints actually? So we see here there's some hint here them give us, so we can translate this problem to another problem. Will be sum of on of lambda here will be like, yeah, sum of will be lambda I, and multiply with the constraints. Will be on function for constraints. So we might have a constraint like will be like xi yi. Sorry, we will multiply with the dot product with x I and plus p and minus 1. Oops. Sorry, everybody for this. I don't know why my slide is so. When I'm writing something, it look like something ugly like this one. I know. It's really. I'm really sorry about this problem. Okay. But by the way, you can write in something like this one. Try to minimize this function by the constraint like this one and the lambda I. That will be running from our, for example, like in our training set we have like n data point, and then we're trying to solve this problem actually. So we can say our Lagrange we now equal to this problem. Sorry. So, okay, great. On the pen. But actually we are in the slide, so I don't know how to write it on pen. Sorry. So we try to do this one, and yeah, I will try to rewrite it in some with this to prove this one. Actually, for you to do this one. Sorry about this one. Okay, so we might have yeah, we now can have an formula like this one, right? Okay, so we understand us with this kind of functions. We can use some partial derivative, right? For example, like we can use in our we can compute our Lagrange functions with the partials derivative for w. Then we can get something like from by this one we can have like w, right, minus all of this. Okay, right. So now based on the partial derivative for the w, and then we can rewrite this one to this, and this one we have to have another thing, right? So we will have like, okay, I will have actually lambda here. I'm writing this incorrect way. Okay, I have to. We will have by lambda I. Lambda I. We'll rewrite this one by the way. So here we can have like the constraints here. Then I have to write something. So okay, psi plus b okay, so now I can derive this one by because we have here will be yeah lambda I multiply with yi, okay, xi, right? Right. So we have anything here to rewrite for this one because we multiply this one and so it will be 0. And how about this one? No, there's nothing to write here anymore. So we can try to minimize this one by controlling for this formula actually. Okay, right. Then we can imply that W will be equal to the sum of on I. Sorry about this one. Lambda I. Sorry. So we can translate to this formula, right? So we can rewrite like W will be equal to the sum of on I with lambda I where I'm xi, right? So we can write this here. The I, yi, and xi. Okay, great. So we can prove something very important for us to learn about the supervector, which have to minimize this function w y vector x in the y vector that we have. And also we in this function we might have another thing to be minimized is will be the value p on the bias of the function as well. So we can have another materials function for derivative for the value p as well here will be equal to. So this one will be equal to 0, right? So this one will be like 0 here. So we will have like something like lambda I multiplied by p. So we will have something and yi here as well. So we will equal to the sum of on lambda I multiply with yi and yep. Okay. that on. So we will have it equal to 0. Okay, then we will have here some formula like this one to try to minimize this one. Okay, so we might we are now in the okay, so time for a break. After the break, I will show this formula to see how to use the Lagrange multiplier to optimize for this ways better with this kind of functions. How we can do this one, and yep. So well, so hope that now everybody will have a very good break, and we'll come back to the second session with a very good mind, right? Okay, so in the meanwhile, so hope that you will enjoy your break and yeah, trying to make it. Hello, everybody. Welcome back to the second session of the lecture today about Spock Vector machines. And I hope that everybody have a very good break during this 15 minutes in very short time, right? But hope that you are already enjoying this one. And also, yeah, I know this lecture about Spock Vector machine is very lots of things like mathematics like this one to do, but you know, like in AI, for example, like we had to do something with mathematics like this one, and yeah. At the end I will show you some application could be like to encourage you, like of course Spock Vector machine will be maybe in somehow it will be dealing with non-linear data will be better than virtual machines, for example, like this. So okay. By the way, I want to I just want to check if you are already come back. Everybody?
Yes, sir.
Okay, thank you. Great. Okay, now we have two formula here, right, where we can derive from the function using the Lagrange function like this one. So, okay, so now the time to use the two formula to replay this to the in the main function where we will have 0 here, right? So now our Lagrange function will be equal to 1 divided by 2, right? And multiply with this one, right? Because we now we have a way to optimize our wave vector, where it will be like so it will be a sum of, normally it should be the square here. That means we have to make an only in iteration I. Then we make an assumption on this only in this filter vector I, but somehow we want to increase our model for other filter as well. So this Lagrange will be, it's my searching for the different filter, like for example, like I plus 1 or I and j will be different with I, something like that, and then we can rewrite this one by first it should be lambda of lambda I yi and xi. Okay, great. Another, and I told you, like it's maybe better if we have another filter vector and this with this constraints and the lambda to learn as well. So we might have another filter vector j, yeah, and this applies the same thing when we compute this one, and we might have yj multiplied by xj as well. Okay, great. So we have it's here, right? We replace this formula 1 to this one, and then we can have like this. Okay, and then we minus. Okay, when minus because we now we can rewrite our something here, the way here as well, right? So we will have like another sum. So lambda I and yi xi multiply, we will have I here, yeah, multiply with another thing, j, where we will have lambda j y j x j. Okay, so we will have what here we have. So we will have like something here, right? we can rewrite this one like this and do something else. At the end, we will check this formula. Okay, so the sum of the lambda I yi plus e and plus this one will be I sum of on the lambda I. Okay, because we have lambda I here, it will be here, right? So we will have different one, lambda I, yi, and p here, right? And not plus here, it should be multiplied here. So, okay, sorry. So we will have like here lambda I, yi, p, okay, and our will be like lambda I, yi, xi multiplied with lambda j and yj's and another xj's will be for in this case. Okay, so we well, it's all ugly. So I don't like this one, but I have no choice. Xi, yi, xi, lambda I. So I will have to rewrite all of this one. Okay, I rewrite this one. But so okay, so I'll go to next slide. So I can rewrite this one until the end. It will be like function L equal to, right? So we will have like the sum of all lambda I, right? Where and then we minus by 1 divided by 2 sum of on the I, sum of on the j here. Lambda I, lambda j, y I multiply y j, and then x I multiply with x j. Okay. Yep. So we can transform our formula there until here. I would like to rewrite this one. It's something here. Because like it's like the same here, right? It's the same here. So this one minus, right? So minus this one, it will be like one and a half here and 1 here. So it should be like minus 1 and a half. And here will be like lambda I, yi, and b. Because we have our yeah, actually we will have another thing to minus. It will be the sum of lambda I and yi b here. But actually this will be equal to 0 because it's based on the formula 2 here, where lambda I multiply with yi will be equal to 0. So we won't have this anymore, right? So we can rewrite this one equal to sum of lambda I minus, I don't like this, okay, then 1 by 2 I have divided by 2 divided by 2. Please. Okay, 1 divided by 2. And we will have the sum here of all what we have. At the end. Xi next day. Okay, right. Okay, so at the end we will have this kind of formula. We are saying that this will be for this one will be so we will have 0, 1, 2 here, right? So here we will have like formula for 3. Sorry. Please. So I make something like this. Okay, by the way, we will have formula like this one. Okay, right. So we and then we will have this kind of formula with this Lagrange multiplier, and what we try to to optimize and then we will have some, we compute somehow with this we update this with our lambda that will be the parameter we will learn in our training sets. Some vector vector here, xi and xj. We also have it's in the training set as well, right? With some vector we are on we have in our data sets. And yi and yj, yeah, of course we have the digest which is like positive and negative class for this one. And what we are learning, we will learn like something like lambda I and lambda j, we can say something like in some slide, for example, like because here is what I'm trying to do. We are using the parameters like lambda, but somehow in some slide or in some book they are writing this one like the alpha. So the meaning of alpha and lambda here is the same thing that we are using to multiplier to the this Lagrange Lagrange functions. Yeah, alpha on lambda is will be the similar meaning in this case. So what I'm trying to solve here is what I can learn in using this to optimize this Lagrange function is will be equal to what in the original function that I would like to optimize by the end. I will learn some value like some from some lambda or alpha will be learning during our training stay or something like that. And with this kind of formula, we can calculate this kind of we can calculate the lambda as well. Yeah. Yeah, here is the main thing that support vector machine is using to update. First, we will have something like our ways. We will update with this formula where we will have some lambda I, yi, and xi we have in our training sets, right? So we had to learn is we could we can make in the beginning the lambda should be like alpha I here will be like 0, and then we were trying to update this lambda this lambda is by calculating this formula, and also what we are trying to learn more in will be like we can use this to update the wave vector as well in this case as well, right? Using this formula. Yeah, that is the main thing that super vector machine will doing. He optimize this how to build this model, and how we can update the way or something like that. Yeah, I will show you in the case of iris data, and I am trying to build a model like yeah. So we should talking about this. So first what we are trying to do until now, like we to try find an hyperplane or the decision boundary, which we are already see like a line like this one, to be best separate the data set. We have like some feature like x1 to xn, and where we have, for example, like two class in the problem of binary class, where we only have like two class like positive and negative, and then try to build this hyperplane. We are now have to do this, right? Actually, we will what we are doing. We will going to set on wave vector, and we know how to transpose the wave vector to at the end for this decision boundaries. It should classify all the point correctly with this formula. You know, like that means we for example, in case of we had negative class, and then we will have this one will be changing to smaller than 1. If we have a positive class, then we will have something like it will be greater than 1, like this. And for the support vector, it would be something like here, like it would be equal to 1, 0 here, right? So we yeah, okay, something like this one. And what we're trying to do is to minimize this wave vector. Actually, as I explained you, there are some how to calculate on from support vector, and then how can we calculate for distance from the positive plus and negative plus, which is the data point will be closest to the machine with the distance, and then we prove that we had to minimize this wave vector formula actually, and what we're trying to bring this at the end will be this formula, right? So and I also show you how to update the way and how we can put some alpha lambda multiplier which constraints to the Lagrange function to optimize this way better. Somehow I improve this. So in the super vector machine, we can have different problem. Yeah. And with this different problem, different techniques actually. And with these different techniques, we will have different way to dealing with this kind of support vector machine model. Where we, for example, like first we will have something like we say something like dual form problem. And then we go to submarine problem. I will tell you what is that later, and finally it will be on kernel functions. That's something like we can dealing with nonlinear boundaries, something with nonlinear dataset. I told you. Okay. So first we go into dual form problem. Yeah, actually We see this already, right? So what we are trying to do, we maximize the weight better by minimize the function using Lagrange multiplier. And at the end, what we can transform from using this alpha or lambda I, and then we can have this formula after we changing our form using how to update the way, like it's more or less like this one, right? Yeah, it is this one. It's not more or less. Actually, like we will have like some lambda I minus 1 divided by 2, and the sum of all of the lambda I, lambda j, yi, yj, and here either it's actually here will be on transform the transform vector of transpose vector of xi and xj to make to actually we yeah so more or less it look like that, and yeah. So with dual problem, what we are trying to do, what we optimize at the end will be trying to maximize this the way of this alpha actually. Okay, so we have something here. That's actually we already have this one, right? How we can update the way here will be lambda I the sum of all lambda I multiply yi and xi. Where we can see we prove this here, right? So on the w will be updated by this function this sum functions. Okay. So what we were trying to do, we somehow we can maximum the alpha because we have the formula, right? So this could be on a way how to do that, and we also set this alpha from the beginning. We can set it to 0 or something, and then we recalculate this alpha again and again by using the maximum function with where we will calculate it again and again with the y with the here we might have something. Okay, so yeah. Okay, so let's go to for example, like to see how actually how we can use this what's Lagrange multiplier optimizations to apply to our iris data, right? Where we are only build on virtual to update our way to solve for the last problem. And now what difference between if I use an SVM dual problem, and then it's better to with the problem of perception or something like that or not. So okay, so let's come back to the problem of iris data. Now I can share my screen. Yeah, so you are already see this problem, right? Where we have an data set on iris data, where we have in the first 50 sample will be Setosa class, and another 50 sample will be in the vesicular class, and another cities sample in the Virginica class. Yeah. And from what we are doing last week, we can have a very perfectly perception model to classify for Setosa class and particular class, right? You are remember about this one, right? When we build our perception, and then we can have in the Setosa and vertical color when we test, we make how our hyperplane can be working with this test set, and then we see that we can make an very good hyperplane because we have this to the set is quite separate, right? So that's why for this our perception quite simple, but it will be also like we have a very good result like this one. We have like 100% of accuracy on the test sets. By the way, yeah, here is the result from the test sets. So good, very good. But we also see in the beginning the errors of the misclassification quite high here, but from the iterations like 2, and then it's go down like 0. So that means, oh, okay, from this iteration 2, then my perception model will have a very good result on this one. So very good, very nice. But in the class of physical and Virginica model, class, we see that this class physical here, for example, like it might be -1, Virginica might be 1. So we have some data will be like it will be overlap together in it will be overlap in this space, right? So it's now this problem is will be very hard to classify some kind of this data, and you see some errors here, like they make an hyperplane and there's some wrong decision here, right? This one should belong to this class, and in here it will be more harder, like the hardest one, like the two class will have the same feature projection on this two-dimension space. So wow, it's so hard, so hard to classify this kind of data set. So now I think this version is not enough to make a very good prediction or classification on this problem anymore. So I had to build another. But by the way, we can see some errors will go down from until like, because it looks like the misclassification here will be in the beginning, like 24, and then it's go down until like more than 10 here in iteration 6, and the epoch 6 here, yeah, and it's my yeah, at the end we will have quite good with the lowest one here. Okay, so here the SVM model that's I built on the what we are learning today about like dual problem when we will update our way using the formula that I already showed you, right? And also how update for the alpha or the lambda using the Lagrange function to optimize this one. Then I can make an SVM model will be, you see in the vertical one, right, where there's some machine class here, right? So they make an hyperplane like this from perceptron using perceptron, but now you see the hyperplane will go to another directions like this one, and of course this one is still hard to be shown, but at least we will like to fix this problem on the test prediction phase. We will fix this problem with projection, like we don't have any misclassification here anymore. So right. So but this one still hard to be classified, right? If you can draw something like I don't know, somehow like this, somehow like, yeah, we can train our model, and at the end we can see how the best one will be somehow it will be classify the two point here, because it's also hard to classify some filter that will be overlapped like this one in the real case of our real data, real work. And this happened, I think it's happened in many real data as well. For some case, like another class will be lie on will be overlapping like this one on the another class, and so that's why we will use another things in subvector machine like kernel functions, submax marking problem to improve this one, try to improve this one. And I hope with that kind of theory, and then we can show that problem with some kind of data like very hard like this one, right? Okay. So come back to the course. I might have an SVM model where I will yeah. So here the way I'm create some SVM model. Yeah. So this one first, and well, we are now in the dual problem where we might have like linear classifier, but actually this one will use some kernel here, by the way. But I will explain about the kernel in maybe in the next lecture. Yeah, because the kernel here will show from the problem like Somerset will be another class will be overlap or lie on will be placed on very close to another class like this one, like this one, like this. This is also how to for the machine learning to learning about this one. And okay, so actually in this SVM I will have several parameters to set up at the beginning. Like I will have some how many iteration that I want to train for the model, or how to run for the model. So now you don't care about this one. So what I want to do, I will have an alpha, yeah, will be on NumPy array, right? And I also have a way better will be a NumPy array as well, and I will have another will be the bias array will be a NumPy array better will be initialize will be array of 0. And with the iterations, and I want to learn for example, like I put it here 100, and then with this I love these iterations until and then I update this for example, like I will find in on the dataset, because we have the dataset will be the set of the training set here, right? So I will run this from on the sample in the training sets, for example, like that, and I will create with this J. Then I will find another I number I position will be similar, will be different with the position of J. Actually, when we see in the formula, we already see here, right? When we we have an is an exercise, something like that. So yep, I will have filter vector of xi and xi, and I will have also the label of yi and yj as well. So now I have some kernel, but I think you will know next in the next time. But okay, so what I want to do here I will update this alpha by the methods of that we already see, right? And but then I will also calculate the output will be in our from our training set, and we will make a dot product with the way in the bias will be calculated here, right? Okay. Yep. I will explain you about the kernel function where we will have like linear and polynomial quadratic kernel some radius basis functions. Yeah, I will explain it for you next time about this one. But yeah, here you see like SVM will be like look like more or less will somehow give us or maybe better way to dealing with non-linear data in separable or in separable data like this one. Some this kind of this. Okay. So I think today that's on what I want to say in with you. Yeah. So that's you you will yeah, gain some idea about what is superconductor machine and what we are doing with it like this. Hope that you enjoy this lecture, and yeah, you might with me use this kind of what you are understanding to try to implement for some, yeah, on very simple SVM machine learning somehow to deal with this problem. Okay, thank you for attention, everybody, and listen to this lecture. So do you have any question until now? Somehow to want to someone to want to communicate with me or something. Otherwise, we will stop our lecture today, and we will see each other next week, right? Because yeah, I would like to say a little bit about the final, right, where we will have the final lecture in the 4th of June, right? Then we had the 2 week, sorry, until now to go to the final. So hope that everything will be fine for you, and yeah. Okay, if we don't have any question until now, then we can stop here, and wish you everybody on a very good weekend. Enjoy your weekend, and bye bye.